So for our final problem, we're going to do a thin film interference problem. So this is question number 29 in the textbook. And the problem states that a thin film of magnesium fluoride, N equals 1.38, coats a piece of glass. So we're going to note that N is equal to 1.38 because that's probably going to be useful eventually. Constructive interference is observed for the reflection of light with wavelengths of lambda equals 500 nanometers and 625 nanometers. So we have lambda 1, I'll call it, is equal to 500 nanometers. And then we have lambda 2 is equal to 625 nanometers. What is the thinnest film for which this can occur? So we want to know what is thinnest T value we can have. So the first thing we're going to want to do is take a look at our thin film interference equations and figure out which ones we're working with. So we have two equations. We have 2t, so twice our thickness is equal to m lambda over n, and we have 2t is equal to m plus 1/2 lambda over n. Now the tricky thing about thin film interference is that either equation can be constructive or destructive depending on what the situation is. So we know that we have constructive interference for a couple of lambda values, but the key thing is how many phase changes do we have. So if we have 0 or 2 phase changes, we're going to use the top equation. If we have only one phase change, we're going to use the bottom. So if we read through the equation the question carefully, it says a thin film coats a piece of glass. So if we think about what's happening, light is going to be coming from air, and it's going to hit the film. And we're going to have a phase change for light that reflects off of the film, so the air-film interface. So air film interface, that's going to give us one phase change. Then also we're going to have to think about the film glass interface. So because light that reflects off of there will also undergo a phase change, so we have another phase change. For a total of 2 phase changes. So which tells us the equation we're going to want to use is 2t is equal to m lambda over n. Now ultimately what we want to know is our thickness, but we're going to do some math before we can get to that point. So we know that the thickness is going to be the same for either wavelength value, because we're looking for the thinnest possible wavelength that satisfies both of these conditions. So what this tells us is that m1 lambda 1 over n is equal to m2 lambda 2 over n. And again, this isn't necessarily intuitively obvious, so kind of the way I got to this was we have a particular thickness that's satisfied by the equation m lambda over n, and we know it works for 2 different lambda values, which means it also has to work for 2 different m values because n is just a constant. So I'm going to say m1 lambda 1 for one of them, and I'm going to call the other one m2 lambda 2. We can see from this equation that the n's are going to cancel out. If we multiplied both sides by n, we'd get rid of the n's. So we will be left with m1 lambda 1 equals m2 lambda 2. We don't know what the m values are. That's kind of what we're looking for here so that we can plug into our equation to find thickness. But we do know lambda. So we'll have m1 times, we said lambda 1 was 500 nanometers, so 5.00 times 10 to the minus 7 meters is equal to m2 times, and then this one was 625 nanometers, so 6.25 times 10 to the minus 7 meters. From here, it's kind of a matter of guessing and checking, seeing which m values are going to work. Now, if you look at our numbers, we can see that m1 is going to have to be bigger than m2 to have a valid equation, because it has a smaller wavelength. So if we want these numbers to be the same, we're going to have to pick m1 greater than m2. And we can see immediately that if we tried, the natural choice might be to do m1 equals 2, m2 equals 1. But that would give us, 1 times 10 to the minus 6 on this side, and then on the other side would have, on the right hand side would have, still have the 6.25 times 10 to the minus 7 meters, so that's not going to work. So you can guess a few values. Kind of what I do is, if you look at the 6.25, we're going to have to make some way to make that into an integer, because integer in the loosest sense of the word, because it's not really an integer, it's a fraction. But you have m1 times 5.00 times 10 to the minus 7. That's always going to be multiples of 5, so 5, 10, 15, 20, 25. So the smallest value that's going to make 6.25 into something like that is going to be m2 equals 4. And again, you don't necessarily have to observe this. You could guess and check, picking different m1 and m2 values, but if you make that observation, it might make things a little bit easier. So we're going to try m2 equals 4 and m1 equals 5. So this is our guess. So if we plug that in, we're going to have 5 times 5.00 times 10 to the minus 7 meters equals 4 times 5.00 times 10 to the minus 7 meters. This side will give us 2.5 times 10 to the minus 7 minus 6. And this side will also give us I wrote the wrong number in here. Let's back this up for a second. Alright. So this one should be 6.25. Otherwise, it would not give us what we need. This will also give us 2.5 times 10 to the minus 6 meters, which is good. That means we found our m values. So the last thing we need to do is to find our thickness. So we're going to go back to our equation for constructive interference for two phase changes, which is 2t is equal to m lambda over n. We want to solve for thickness, so we're going to divide both sides by 2. We'll have t is equal to m lambda over 2n. You can pick either m1 and lambda 1 or m2 and lambda 2. You'll get the same answer either way. I'm going to pick m1 and lambda 1, but you could also do the same thing with m2 and lambda 2. So now let's plug in our values. We'll have that thickness is equal to m1, we said was 5, lambda 1 is 5.00 times 10 to the minus 7 meters. I'm going to divide by 2, and then our index of refraction, we were told, was 1.38. Plug this into our calculator, and we will end up with our thickness is equal to 9.05797 times 10 to the minus 7 meters. Now you have to think about sig figs, and we have 3 sig figs in the index of refraction and in our wavelengths, so we're going to keep 3 sig figs. So this would be 9.06 times 10 to the minus 7 meters, or 906 nanometers. And once again, it doesn't matter whether you write it in meters or nanometers. Either way is acceptable. And so that's how you do question number 29 in the textbook.